Can the flow of time split? Can it form different branches, loops, or wind around itself? If the answer is yes, then time travel is something we must take very seriously, because Einstein's equations allow for travel through time. Today we're going to explore how time might be far more complex than the ticking hands of your watch. Stick around until the end to find out. What is time? For us physicists, the distinction between past, present, and future is nothing more than an illusion, albeit a persistent one. Subjective time, with its insistence on the present, has no objective meaning. We often define time as a physical quantity that describes the sequence of events in a clear and irreversible direction. The cosmos itself moves not only through space, but also through time, from the Big Bang to its eventual end. Time is what prevents everything from happening at once. We experience the passage of time as irreversible. The future can be changed. The past cannot. The two are separated by the present. So far, so clear. But the deeper we look, the more we discover that time is not as simple as it seems. From a physics standpoint, time is one of the most difficult concepts to define. Einstein showed that time is relative. Gravity and acceleration can stretch it, so time on a mountaintop runs slightly faster than in a valley. To understand why time remains a hot topic, we explore two areas: Einsteinian physics for the large scale and quantum mechanics for the tiniest scales. These two systems often contradict each other. Consider Schrödinger's cat, a cat in a sealed box with deadly poison that might be released at any moment. Since there's no outside observation, the cat is both dead and alive, in superposition, until someone opens the box. Schrödinger devised this to highlight the incompatibility between quantum mechanics and classical physics. Quantum theory says a system can exist in multiple states at once, and only chooses a state when observed. Applied to a cat, this feels absurd, but it's the strange reality quantum theory suggests. This is where our intuition clashes with the math. Beyond superposition, another bizarre phenomenon is entanglement. When particles interact, their states become interconnected. Two entangled electrons generated together will always have opposite spins, even if separated by light years. Once one is measured, the other's state is instantly known. This defies locality, the idea that a particle is only affected by its immediate surroundings. The exchange of information appears instantaneous. Einstein called it spooky action at a distance. Does time even exist? Entanglement forces us to ask that question. In quantum mechanics, time appears as an external parameter, but that creates contradictions with relativity. Scientists at the Italian National Research Council re-examined an idea first proposed by Page and Wootters in the 1980s. Their idea, time arises from the relationship between one object and another that acts as a clock. In other words, time is not absolute, but something that emerges from within a quantum system. Next, how experiments and mathematics explore a universe without external time. Recap. If the universe is a closed quantum system, we can split it into a clock and the rest we observe. Although the full system is unchanged overall, correlations between the clock and the system create the illusion of time passing. From an internal observer, time appears real. From the global view, time is absent. In a non-entangled system, the universe is frozen and unchanging. When parts are correlated, an internal observer perceives evolution. Time emerges from correlations. This is the heart of the Page-Wootters mechanism. Researchers at the Italian National Research Council applied this mechanism in a test model. They used a vibrating harmonic oscillator together with tiny magnets acting as the clock. The system was described with Schrödinger's equation, notably without any explicit reference to time. When calculations were repeated using larger macroscopic objects, the math simplified back into classical physics. This suggests the flow of time could be a result of quantum entanglement even for large-scale systems. Their conclusion: start with quantum physics and explain how classical physics emerges from it, not the other way around. But caution is warranted. Not everyone agrees. Some scientists are skeptical. The math is sound, but will it produce anything truly new or useful? It remains an open question whether this approach updates quantum physics or general relativity. If time can split, imagine branches or loops, alternatives that diverge from a shared past. These branches could correspond to different correlated histories within a quantum universe. Or time might wind around itself, creating loops under particular conditions permitted by general relativity. Einstein's equations allow for solutions where closed, time-like curves, loops, exist. That means time travel must be taken seriously, theoretically. but paradoxes and consistency constraints remain difficult to resolve. If time is emergent, our everyday experience, cause and effect, aging, memory, would be a consequence of deep quantum correlations. It reframes how we think about the universe, not as something unfolding in time, but as a web of relations. Experiments at small scales are possible and informative, but scaling results up is the big challenge. The best path forward is careful experiments and mathematical work to link quantum to classical behavior. That will tell us whether time is fundamental or emergent. The idea forces us to rethink what time really is, a profound shift in perspective. If you find this fascinating, you are in good company. If you found this fascinating, don't forget to like and subscribe for more deep dives into the mysteries of the universe. Stay curious, and remember, the answers are out there, if you keep looking up. Thanks for watching. Sources and further reading are listed in the description below. Stay curious.